to go back a bit because I really dislike how the textbook covers the order that it covers this idea of how are the electrons attracted to the nucleus. It like hits it at the beginning of the chapter, but you don't really need it till the end of the chapter, and it just feels very disjointed. So I'm going to come back to here and re-emphasize kind of these two slides and what we're going to be looking at, because it's going to play into everything we're going to talk about today, which is size and ionization energy and electron affinity, and how we can determine how different atoms compare with those quantities, and also how we can use the periodic table to guide our understanding of, how do two atoms that are next to each other compare versus ones that are in the same column and stuff, okay? So there are three big factors that go into all of these three categories. And I'm just going to write it on this slide because I have room here. But the three factors, let me make sure I'm putting this in. Yes. Okay. So the first one is going to be the shell. By this, I mean, are we at the valence electrons? Are they at n equals 1, n equals 2, n equals 3? Okay. Then we're going to look at the number of protons. So if we're comparing two things, this is kind of an order of priority of the characteristics we're going to look at. So we have two different elements, let's say, two different types of atoms. We're first going to look and say, are they in the same shell? And when I say they, I mean the valence electrons. Then if they are, then we're going to go to the next thing on the order of priority, the number of protons. And then finally, we're going to look at any electron repulsion. Okay? Now, your book talks about this in a few different ways, but this is like the end-all be-all that when we're reviewing and people are like, I keep getting lost about how to tell which one's bigger. I'm like, go through these three things, and if the first one applies, here's how you know the answer. If it doesn't, go to the next one. Here's how you're going to use that answer. And I think that I've found this is the easiest way for you guys to actually answer the question, not just understand the concept, but actually answer the questions. Okay, so we're going to keep coming back to those three characteristics. So applying those three to the concepts that they're based on. So the shell, if you have electrons that are out further from the nucleus, they are not as attracted to the nucleus. Okay, the further something is away, the less attracted it is. So if you have something that has valence electrons at n equals 2 and something that has valence electrons at n equals 3, those ones at n equals 3 are less attracted to the nucleus. End of story. Now, when we talked about this earlier, we talked about this equation and it felt very complicated. It's just that R value. Okay, the shell tells us how far those electrons are out. The further out they are, the higher in energy they are, and therefore the less attracted to the nucleus they are. So I'm going to summarize that down here, I think, and then maybe we'll copy and paste it. Okay, so as the shell, as N increases, energy is going to increase, and attraction to the nucleus decreases. Now, if you look at the reading, this is where this idea of Z effective or the effective nuclear charge, that's where this comes into play. Because if we have two elements that are down a column from each other, so for example, grab a periodic table, that's how I want it to look. This one's good. So if I have, I'll use these two I've circled already. If I have rubidium and cesium, you might initially think to look at the protons, but that is number 2 on our list. We're first going to look at the shell. Because even though cesium has more protons, and so some people might think, oh, those electrons are more attracted to the nucleus, it's at the 6th energy level instead of at the 5th. And so because of that, because it's at the 6th energy level, it's further out, it's not held as close, and so the attraction is less. It's like, you can think of it as like strength. Like the nucleus, even though it has more protons and you would think it's stronger, they're so much further out that those electrons cannot feel how strong the cesium is. So a lot of that is due to this idea of shielding that we talked about. When you're at the 6th energy level, you have 5, 4, 3, 2, and 1 all blocking, those electrons are all blocking that outer electron from feeling the nucleus, okay? So this is why we have to first look at the energy level. That's why it's number 1 on our list. Because no matter how many protons there are, if there's a bunch of layers of shielding in the middle, that's going to make it really hard for those electrons on the outside to feel all of that positive charge. Okay? So that's why the shell is going to be the first thing on our list. Now, if you go through some of the problems in the textbook, might talk about this. I will not ask you to calculate a Z effective, okay? But if you run across it in the homework problems, Z effective, you basically just subtract off the core electrons. So what it means, remember Z stands for the atomic number, which is the number of protons. So if I've got helium and lithium, so I'm going to use those as my 2 examples. Sorry, not helium, hydrogen. Hydrogen has 1 proton, and it is at n equals 1, so there are no core electrons. That's its only valence electrons. Lithium has 3 protons, but its valence electrons are at n equals 2. So an initial thought might be lithium is stronger because it has 3 protons. And that generally is true. The number of protons increases, the stronger that nucleus is, and the more it can pull and hold those electrons in. Okay? But if you're at different energy levels and you have that layer of shielding, then that charge is not going to be felt fully. And we can quantify that. It's not perfect, but it works pretty good by taking the Z, the number of protons, and subtracting off the core electrons. Let me just, if I cut this, am I gonna, yes, I should be able to save it for later. Okay, so when we look at the number of protons of hydrogen and we think about those number of protons as the strength holding the electrons in, it's got a +1. When we look at lithium, instead of thinking of it as +3, we're going to use this equation and subtract off any core electrons. So if we're at n equals 2, just draw a quick diagram for you. This is lithium, right? So these 2 would be our core electrons. So we're going to take Z, which is 3, the number of protons, and we're going to subtract off those 2 core electrons, and that leaves us with a Z effective, or like the actual useful positive charge that has a pull on the electrons of 1. So the electrons in lithium, or the electron, the valence electron, feels the pull of the nucleus similar to how hydrogen's electron feels its pull. They both have a charge of 1 when we account for that shielding of those core electrons. Let me do one more to get this point across, and then we'll apply it to size and stuff. Okay, so sodium is right below lithium, and it has a positive charge of 11. It also has 11 electrons, right? But that's its nuclear charge is 11. Okay, so going back over here, sodium has a positive charge of 11, and its outer electrons are at n equals 3. Let's draw a quick orbital diagram so that we remember what it looks like. Okay, so it has 1 valence electron and 10 core electrons. Okay, so the positive charge that is going to be felt by this electron here is Z11 minus those core electrons, so it equals 1. So what you're seeing is that in a given column, hydrogen, lithium, sodium, they have a similar Z effective. Every time you subtract off those core electrons, you still get this effective nuclear charge of +1. So even though sodium has 11 protons and lithium only has 3, sodium does not pull on the valence electrons any more than does sodium because of that shielding. Okay, so this idea here, that those inner electrons are blocking the ability of the outer electrons from feeling the nuclear charge. So that's where this idea of Z effective comes in. So what that does so conceptually that's important, but what that does, how that translates into answering a question about two different atoms is going to be look at the shell. So that's why that's our number one thing. Let's look at the shell. Okay, so I'm gonna copy our list down here. Can I rotate that? No, it doesn't want me to do that. Okay, so I'm gonna copy our list down here so we can continue to talk about this. So the shell is our number one thing we're gonna look at, and maybe I need to emphasize that by like putting number one. So these are in order of priority of how we're going to address these different factors. Okay, the second thing is the number of protons. We only look at that if we're in the same shell. So for example, instead of looking at, you don't need to go back with me, I'm just pulling up a periodic table. So instead of comparing hydrogen, lithium, sodium, let's compare lithium, carbon, and fluorine. Okay, because remember, if they're in the same row, that means their valence electrons are in the same shell. So you got to get to the point, I'm hoping you're there already, but you got to get to the point where you're comfortable looking at the periodic table and getting that a row means the valence electrons are in the same shell. And that a column means that as you go down, you're adding a shell, but you have the same rough valence setup. So in the first row, all of the valence electrons are just 1 in the s orbital. In the second row, there's 2 in the s orbital. It's just that, is it the 2s or the 3s or the 4s, but they're all 1 or 2 in the s orbital. In the third row, you've got 2 in the s orbital and 1 in the p orbital. Okay, so recognizing that info that you can get from the periodic table is crucial. So lithium, carbon, and fluorine, let's focus in on those. So lithium has 3 protons, carbon has 6, fluorine has 9. Okay, so let's take those examples down here. Lithium is +3, carbon is +6, fluorine is +9. And all of these guys have their outermost electrons at n equals 2. If we were to look at the orbital diagrams, and draw a small one for each of these, so you can tell, and if you're moving on to Chem 2, you're going to be able to tell that this is something I am going to use very frequently. It's like, let's look at the orbital diagram. The more comfortable you get with it, I'll probably say, like, think about the electron configuration, but what I'm actually asking you to do is picture the orbital diagram. So if you're really struggling, then I'll go back to the orbital diagram, but I might not always start with that in the future. Okay? Yeah, so 1s, 2s, 2p, so that's what fluorine looks like. Carbon looks like this, and lithium looks like that. Okay? So they're all in n equals 2, so we've already checked off number 1. So we already know they're in the same shell, so we're not going to use that for comparison because they're the same. So let's go down to the number of protons, okay? And let's compare the number of protons. Now for this exercise, let's look at the size of the atoms. And maybe I'll back up a smidge or go forward, as it looks like. And let me talk really quick about size as we go down? Because we just said that shell is like the most important factor, the one we want to consider first. So let's first talk about how that affects size, and then maybe when we go across where a shell stays consistent, maybe that will kind of build on that, okay? So as we go down, remember the Z effective, the number of protons is not particularly influential, because even though we increase the number of protons, we also increase the shielding, and so that doesn't help us very much. So all we're looking at here is the shell. So this guy's at n equals 2, this guy's at n equals 3, this guy's at n equals 4. That should be apparent pretty quick that if I'm adding a shell every time, the atom's going to get bigger. Okay? Those electrons need space. So if I have one layer of electrons, that's going to be a smaller atom. If I have 2 layers of electrons, that's going to be bigger, okay? And that's why we see the size increasing as you go down a column. I don't remember if this picture is from your textbook or not. If it isn't, refer back to it, because you're going to be able to base all of the other properties, the ionization energy and the electron affinity, off of size. And I think it's so helpful to visually be able to see how the atom sizes change, okay? So first point, as we go down a column, the atoms get bigger. The reason is because the shell is increasing. So down a column, increases in size because N is increasing. Okay, now because I already have this up, we'll look at the trend and then explain it instead of explaining it and then looking at it. So again, let's focus on the second row, n equals 2. Second row, second shell of electrons, 2 layers of electrons. I like calling them layers. I haven't done that before and it sounds like, I don't know, more understandable. All right, second row. And as we go across, these numbers down here are the size in picometers. Yes? So as we go across, you can see they're getting smaller. You can see it in their numbers. You can see it visually. Okay? So as we go across, this decreases in size. And we don't know why yet. We're going to explain that. So what those 2 trends really tell us is that this corner of the periodic table, that's where stuff is small. And this corner of the periodic table, that's where stuff is big. The atoms are big. So some people, some teachers try to like the whole arrow going down, arrow going this way. Yeah, that's a little bit confusing because like we always talk about it as like stemming from that top left-hand corner, but like one increases and one decreases. So I think if you think about it as the corners of the table, then you can understand the increases and decreases. If this guy is big and that's small, what you mean is that they get smaller going up and they get smaller going across, or they increase going down and decrease going across. If you just kind of keep those 2 sides in mind. And when you get the test on Friday, rip off the periodic table and write small in this corner and big in that corner, okay? Like anything that you can spew out onto your periodic table, the second you get it, the better. Okay, because there is so much information contained in there. Like I would also, with electron configurations, I would write right here 3D and maybe even 4D and 5D. And if you want to be really careful, you can write 4S, right? And 4P to remind yourself that there's that change between the S and the D, that it goes down in shell as you're going across. If you have no idea what the hell I'm talking about, you didn't watch the video, So go back. I'm sorry, I feel like I was a little bit spacey. I got sick like Wednesday night. I thought I was just tired on Wednesday. And then by the time Thursday, I woke up and I was in bed Thursday and Friday and most of Saturday. So if I'm a little spacey on the video, that's why. But we talked about electron configurations and how to use the periodic table to write the electron configurations. And you have to know that the Ds, because they are higher in energy, because of their shape, they come after the 4s, but before the 4p. And the periodic table sets that up really nice, but you have to remember that that's not 4D, even though you're in the 4th row. This isn't 4D because the Ds start at 3. They don't start at 4. Okay, that was a review. All right, back to our size thing. Okay. All right, so we need to explain why do they get smaller as we go across. So we're going to go back to our list. We already said they're in the same shell, so we're not going to talk about that because that's not a factor because it's the same. Doesn't matter if we're looking at these 3 atoms, they're all at n equals 2. So we're going to go to the number of protons. Okay? 3, 6, 9. Looking at their size. 3 is big, 6 is smaller, 9 is even smaller. Okay? This is where this idea of the strength of the nucleus comes into play. All right? Think of the nucleus as literally pulling on the electrons because they are. There is an attractive force. It's the same thing as the Earth's gravity is currently pulling on you. Okay? And if you compare Earth to Jupiter, Jupiter is stronger. It's going to pull on you harder. It's the same thing with the nucleus. If you've got lithium, it's strong to 3 protons. If you go to carbon, it's a little stronger. It's 6 protons, okay? And if we go to fluorine, it's even stronger. It's 9 protons, and it is going to suck those electrons in as good as possible. I taught for a professor, like when I was a TA, who called this electron sucking power. Sure, yes, it is literally sucking the electrons into it. And fluorine is super good at that. The reason is because for the layers of shells it has, right, because it only has those 2 shells, it has a lot of protons for just those 2 shells. So it is actually the best on the periodic table at sucking in the electrons. You would think something with more protons would be so much better, but the problem is then they end up having those additional layers. We don't really talk about the noble gases in this because their size doesn't actually change a whole lot from the one before it, and also, although they're good at sucking in their own electrons, they're not going to grab anybody else's because they already have a full valence, and so it's just easier to kind of leave them out of the picture. Okay, so we've now used number 2 to explain why fluorine is smaller, because, I'll put this in green just like we did with the one above, as the number of protons, I'm going to put this as Z, because you guys should know that Z is the number of protons. If you don't, it is. Z is the atomic number, which is the number of protons, which is what's on the periodic table. So as Z increases, the attraction increases, and therefore the size gets smaller. The energy actually gets less as well. Okay, those are tied to each other. And maybe we'll move this down a little bit so we can talk about size for the shell as well. There's got to be a way to select all without having to just circle it every time and miss things. Okay, so energy also goes down. So on the shell one, as the shell gets bigger, the energy gets bigger, the attraction gets less, the size gets more. Don't get confused later on when you're like, oh, wait a second. Fluorine has more electrons though. Why would it be smaller? Because it doesn't have to do with how many there are. It has to do with the charge on the nucleus and how well it can suck those in. Now again, you can only do this if you're comparing within the same shell. I can't go talking about, chlorine and how many protons it has because its shell is N equals 3. So like all bets are off there. Okay, I love talking about size first because it's going to make everything else we talk about make sense. So if you get confused, always go back to size. Fluorine, super strong. It holds its electrons in tight, and so it's really small. Well, guess what? The concept of ionization energy, so definition, ionization energy is the energy to remove an electron. So if I've got fluorine here that is really good at holding onto its electrons, how easy do you think it is to remove an electron from fluorine? It's really, really hard. Okay? It does not want to give its electrons up because it's really good at holding them on. So things that are small will also have high ionization energies. Now, this is not the energy of the electron. It is the energy required to remove an electron. I'm realizing as I'm about to talk about rubidium, how ironic it was that I went to like a very conservative Christian school, and I remember my professor talking about rubidium, like she was such a whore because she would give it up so easily, and I'm like, geesh, I can't believe he said that in class. So, but now you're not going to forget, right? So rubidium has a low ionization energy, meaning she gives up her electrons really easily, okay? She's a really big atom, and she doesn't have a very good hold on those electrons because she's big and her electrons are really far out, so they're not very close to the nucleus. She doesn't have a very good hold on them, and so it's pretty darn easy for those electrons to be taken away. Now, it does take some energy. It's not like she doesn't literally want to give them away, but it doesn't take a lot of energy to remove them from rubidium. That is a terrible example. This was, long enough ago, I guess, that like we weren't as like culturally sensitive and like, politically correct and stuff. I guess that's what it is. All right, so big atoms, easy to take their electrons away because they're not held on very strong. Small atoms, really hard to take their electrons away because the nucleus is really good at holding on to those electrons. I need to write this in a different color because I need a different color. So we'll use red for the ionization energy. Low ionization energy down here. And this is why I don't do the arrows. You'll have that in your book. Arrow this way, arrow that way, ionization energy, size. Like you can infer from the fact that this corner has high ionization energies. Okay. That must mean that the ionization energy decreases going down, right? They're getting bigger. And so it's easier to take their electrons off. So the ionization energy decreases going down and it decreases going this way. So if you picture it from this corner, they get bigger going that way and they get bigger going that way. That also means the ionization energy increases that way and increases that way. Okay? So take the two corners and go from there. Try not to follow the arrows that the book's going to do for all of these properties. It's like increase, you're just going to be memorizing it then. Okay? So picture this, picture the size of the atom, and then tie these properties of ionization energy and electron affinity tie them to the size of the atom. If you've got big atoms down here, that must mean that it gets smaller going that way and smaller going this way. So even if you're talking about this guy, you still know it goes smaller going up and smaller going to the right. I realize I'm still like drawing virtual arrows. I'm just drawing them from the corners rather than the top right, which is how your textbook does it. Okay, so we're not going to do this because we talked about this already. I should have used this instead of going back. Ionic radius. No, we don't want to go there yet. Hang on one second. Okay, I'm going to skip forward to where we talk about ionization energy so that it's formalized because we talked about size. We're going to talk about ionization energy. We're going to talk about electron affinity, and then we're going to go back and give them a little bit of detail. Okay, so here's the actual numbers for ionization energy. So you can see 520 down here. This is probably in joules or kilojoules per mole. Anyway, it doesn't matter the units, just look at the numbers. It increases. I'm not going to have you worry about these exceptions right now, or at all, actually. I've taught it in the past. It just isn't that important to me. So don't worry about the fact that you get this little dip here and this little dip here. It has to do with an electron repulsion thing that we're not going to worry about. In general, it increases going across. Okay, just like we saw just a second ago, this guy's really small, so it takes a lot of energy to remove that electron. Okay, so it increases going across. As you go down, they get bigger, and so the ionization energy drops because it's easier to remove them from a big atom. Think of, again, I always use this gravity example, but think of like, you know, the like satellites or something that are in orbit around the Earth. Those are in orbit because of gravity, but they're very loosely held. Like if you just knock them off course slightly with like a little bit of power, they're gonna go off floating into space, okay? It is not that easy to take a person and float them off into space, agreed? Because they're held tighter in. So if something's smaller and held tighter to the source that it's attracted to, it's a lot harder to take it away. If you're down here with a big atom that they're very loosely held, those electrons can go away real easy. Okay? Sometimes we'll give you plots like this to show those trends. So here is lithium and here's fluorine. They're showing you that increase in ionization energy. If you look at this row down here, that's a column. So let me put that in a different color. So blue is a row going across a row, and red is going down a column. So you're seeing a decrease going this way and an increase going that way. We could even turn our things around so that we see the decrease away from fluorine and then the decrease away from lithium. Okay, so you can interpret it from a periodic table with the values. You can also interpret it from a graph like this. But again, tying it back to the size is going to be key. And we actually have those plots for size as well. Right here. So in this one, now I'm going to forget which colors I used. I think I used red for the column. So in this one, potassium, rubidium, cesium, okay, we're seeing an increase in size as we go down the column. Same thing with like the noble gases. We're seeing an increase in size as we go down a column. But within a row, we see a decrease. Okay, so be able to read that off a plot to like understand that trend, how it's being showed in a plot versus just shown on the periodic table. We're not going to talk about ions yet. We'll get to that in a second. We already talked about all these trends. This is literally just like putting in words everything I just said. So the definition of ionization energy, how it is, follows the trend based on either a group, so down a column, or a period going across. And this also articulates the why, okay? So larger N, nuclear charge is the number of protons, okay? So this goes back to the same 3 points. We haven't talked about repulsion yet, but it talks about the same 3 points in order that we've talked about here. All right, last topic that I want to address before we kind of dig a smidge deeper into size is electron affinity. And this is basically, it's the opposite conceptually of ionization energy, but the trend is the same. So things that have high ionization energy will also have high electron affinity. So I'll go back to our chart and write that in a second. But electron affinity is just like it sounds. Where do the electrons want to be? How the affinity, meaning like they want to go a certain place. So fluorine's nice and small. It's holding on to its electrons really well. Guess what? Those electrons are being held on really well because they're very low in potential energy. They're nice and close to the nucleus. So if there's another electron around, it's going to be attracted to fluorine more than it would to a bigger atom. The main place we see this happening is metals and nonmetals. So this is great. You're about to understand why nonmetals are going to attract electrons away from metals. Lithium and fluorine. Lithium is big. It's got this electron there. Fluorine is small. It has a spot available for an electron. Remember, this is all filled in. But it has one open spot. And you look at that lithium, and it's looking at things, and it's like, I can be way closer to the nucleus with fluorine. Okay, the closer you get to the nucleus, the lower in potential energy. And so it just skips out and goes over to fluorine. Okay, this is why metals will lose electrons to nonmetals, because the nonmetals are smaller, and therefore they can be closer to the nucleus if they move over there. So we actually move our electron, it joins in here, and we're left with lithium plus and F minus because it attracted that electron. So again, this all goes back to size. So I'm going to go back to our picture of size on the periodic table, and I'm going to say these also have high electron affinities. The electrons really like to spend time by fluorine. In Chem 2, we'll give this a slightly different name. We call it electronegativity, but it's pretty much the same thing. Very slight difference in the definition. Then over here, these guys have low electron affinity. They are really bad at attracting electrons. The electrons are going to move from the metals over to the nonmetals for that reason, because they can be closer to the nucleus over here, lower in potential energy versus when they were with their original metal. There's one more slide down there. I want to see what it is and why. Oh, it's a summary slide. Okay, that makes sense. All right, so the last thing we need to talk about before we're done is what happens when those metals or nonmetals form ions. What happens to their size? Okay, because we just talked about why they form ions. Because lithium and fluorine example, lithium has a low ionization energy. It's really easy to remove an electron. Fluorine has a high electron affinity, So the electron will move from lithium to fluorine for that reason. Once they make those ions, so lithium plus and F minus, we want to at least be able to talk about how that affects their size. We're not going to take it one step further and then talk about like the electron affinity or the ionization energy of that ion, but we at least want to know how it affects their size. Okay, so this chart is a little bit weird to understand, but what you're looking at is that on this side, these are metals that have lost electrons. And so the gray one is the original atom, and the ion that formed after it lost those electrons is the pink one. So if you're comparing an atom to its ion that forms when you're talking about a positive ion, it will always get smaller. This is only if you're comparing the neutral one to the positive one, not like, I don't know, a negative fluorine to a positive lithium. It's not what we're talking about. We're talking about lithium versus lithium plus. Okay, go back to those three things. Shell, protons, electron repulsion. What happens between lithium and lithium plus? Maybe you already know what I'm going to say, but like let's draw the orbital diagram. Okay, here's lithium. What happens when lithium loses this electron? We've just lost an entire shell. So of course lithium gets smaller. It just lost an entire shell of electrons. The same thing is true if you're talking about like magnesium or aluminum. So like let's look at boron. Boron looks like this. It loses 3 electrons. Because that outer shell has 3 electrons that are relatively high in energy. Why are they high in energy? Because it's a bigger atom. So it loses these 3 electrons, and the resulting ion, this little guy down there, is much smaller than its original atom was. Okay, so that's why we have this list. Shell, number of protons, electron repulsion, which we still haven't gotten to. We're almost there. So we compare the shell, and that's how we know that Br3 plus is much smaller, because it lost an entire shell compared to its original atom. Oh, I love this. So we're going to talk about fluorine now. I love this because electron repulsion, we put it at the end of the list, and it seems so like minor. It's minor if something else is different. If we're in different shells, then maybe electron repulsion is not a big deal. If we have different number of protons, maybe electron repulsion is not a big deal. It is a big deal, though, when all those things are the same. Okay? So here is F, and here is F size, and now we want to look at F minus. The shell has not changed, right? We've gained an electron. So in red, we gained that electron. We're still in N equals 2. So we check that off our list and we go to the next one. Number of protons, has that changed? No, it's still fluorine. Fluorine's fluorine. So we check that off our list. Electron repulsion. Okay, that's the only other factor that could possibly affect the size. And check out, the size almost doubles on fluorine. I know I'm really excited, I'm sorry. The size almost doubles on fluorine because of freaking electron repulsion. That's the only reason. So like here's fluorine, it's all fine, it's 72 picometers. It gets 1 more electron, and all of those electrons are like, oh my gosh, get away from me. And they all take a step back because they're repelled by those other electrons that are in their shell. Okay, and then it goes up to 136 picometers. Same shell, it's still N equals 2. All it's due to is the fact that those electrons were squished together way too much already, and then we added another one in there, and they just could not handle being that repelled. So they take a step back, everyone takes a step back, and that gives them a little bit more room to spread out. And you'll see this with every single atom that gains electrons, is that you see an increase in the size now from its original. Okay, last thing we have to talk about, what if we're not talking about a neutral atom and an ion? What if we're talking about like 2 different atoms? So let me get an example. Okay, so we've talked, you can go back and do these ones because they're all comparing a neutral atom, and you can do this one because that's not even ions. A neutral atom to an ion. So these guys are the only ones we haven't talked about. How do I compare magnesium to Cl minus? Same 3 rules. We're gonna look at the shell. We're gonna look at the number of protons. In order, we're gonna do this, and if the first one answers our question, we just skip it. And then we're gonna look at electron repulsion, okay? So Mg and Cl, let's look at where those are at on the periodic table for their shell. Sorry, Mg and Cl minus. Mg is here, Cl is here. When it gains an electron, it's still in the same shell. Agreed? Okay, so it was Mg and Cl, right? Not Mg2 plus or something and Cl minus. It was Mg? Okay, Mg and Cl minus. This one here. Okay, so shell is the same. Even though it's Cl minus, it gains an electron, it's still at n equals 3. Number of protons. Cl minus has a lot more protons than Mg does. Done. Cl minus will be smaller. Okay? I'm really hoping that's true if I go look it up. I don't think the electron repulsion is going to have that much of an effect, but it's possible. Okay, so Cl minus is going to be our smaller atom. Let me look at one more example. Ooh, let's do Mg and F minus, okay? No, that was so easy. We'll do it anyway. Okay, Mg and F minus. F minus is still at n equals 2. Mg is at 3. Done. Shell answered the question. F minus is going to be smaller because it's still at n equals 2. Let's do one more. I'm going to make this one up. F minus and Mg2 plus. Okay, Mg2 plus lost both of its n equals 3 electrons. So they are both at n equals 2. But guess what? Mg has a lot more protons. So Mg2 plus will actually be significantly smaller because of those additional protons. So you're literally just going down the checklist and figuring out which one is going to apply. Start with the shell. If that answers the question, you're done. Okay? And then move on if needed. All right, so we'll spend Wednesday doing practice on mostly chapter 9, and then exam on Friday.